Hello, and welcome to my talk on security as it relates to embedded Linux and IoT devices. Okay. My name's Baillie, and I've been working in the industry for around 12 years. I've been at ByteSnap for about 5 of these. ByteSnap is a electronics consultancy. We do sort of hardware and software solutions. We have over 30 engineers with experience in all sorts, all areas relating to hardware and software. We target multiple OS types from embedded Linux, Secure Next, Windows CE, and bare metal microprocessors. We develop bespoke applications from the ground up, and these are deployed in many different vertical markets. Okay. Right, so the focus of today's talk is security on embedded Linux IoT devices, and in doing so I'm going to focus more on points specific to IoT and Linux, and less focus on what I'd call more general IT security. I will be using a little bit of technical language, but I will try and explain things simply as we go along. We'll be focusing on concepts such as secure boot, lockdown SSH, lockdown communication interfaces such as SSH and UART, and making our applications nice and safe. Okay, so what do we mean by security? Well, obviously, we want a system with no security flaws or vulnerabilities whatsoever. For an IoT system, unlike, say, a server, an attacker is more likely to get physical access to the device. So we need to make sure that anything confidential, user data, cryptographic keys, or intellectual property stored on the device is safe and secure, can't be read off easily or at all. But also for IoT systems, we need to ensure that the functionality of the device is secure. If an attacker gains control of your internet-controlled light bulb, for example, that could be, annoying, or they could maybe get your Wi-Fi password, something like that. If an attacker gained control of your car charger, that could be, quite bad indeed. And if an attacker gained control of an industrial control system, something like a power station, then that could be very catastrophic. So how can we ensure security? So we can do a degree of auditing by hand. This would involve checking through and thinking through any possible vulnerabilities. Are we sending unencrypted data over UDP to perform commands on the device? And if so, do we have plain text passwords, hard-coded and unencrypted? So you can actually ask, your software vendors, if you're buying software, to show proof of their own security auditing as well. So even after all that, you might have missed something. With embedded Linux, you may have hundreds of different open source packages working together. There's a class of software called vulnerability scanners, and what that will do will scan for any backdoors and exploits against open ports. So that the vulnerability scanners, they'll give you any sort of vulnerabilities that are in the system. Then there's a step further where you can do something called binary scanning, and that will actually scan everything during the build of the BSP and generate a report of known vulnerabilities and exposures as present in your software. You can then decide where you need to upgrade for more recent and secure release. Okay. Right, so secure hardware. This is quite an open topic and very context specific to your hardware, really. But there's a few key points we can talk about. The first thing you want to do is make sure your JTAG port's disabled. You can see lots of videos online, lots of blogs online where hobbyists will look for a JTAG port, find it, and then they'll have full access to the system. So make sure you disable that after you finish your tests and your programming. Make sure you do that. That's probably number one. Then the next one, talking about debug UARTs, pretty much any embedded device will use debug UARTs during the design and prototyping stage, but it shouldn't be left in once shipped to customers. If you look online, you can find lots of, again, blog posts, videos of people using oscilloscopes to find these debug ports, and then they find that it gives you a login prompt and that username is root and there's no password, or it's a very easy to guess password. So you really need to make sure that you're disabling the UART port entirely, or at least the input. Actually, a lot of modern security requirements will require any unused interface to be turned off, so you really need to close off the whole thing. Any other test debug points, yeah, disable them if they're not used. An unused USB that's only used for test or debug or programming, disable those. If there's anything you can do to impede physical access to the device, make sure you do that. That can help to some degree. Obviously, it's not going to keep an attacker away forever, but it can help. And you can use something like a TPM, which we're going to talk about in the next section. So a TPM is becoming a common practice to develop secure hardware. The TPM itself is a small chip that can perform cryptographic functions. This can be used to protect your secret keys and perform software and hardware verification. It can prevent cloning and can augment your existing chips' encryption capabilities. And actually, Windows 11 will require TPM 2.0, so it's something you might hear about outside of the embedded space. It's a good way of providing a level of cryptographic hardware to complement a chip that maybe doesn't have everything you need. So consider using this if the SoC you want to use doesn't provide all the security features you might want. Okay, so the bootloader. Bootloader is the first thing that runs on your device. If that's not secure, then nothing is at all. It doesn't necessarily need to be encrypted, but it does need to be signed. So what does signing mean? It means that the bootloader itself came from your company and your company alone. It normally works through public key cryptography, which is where you use a private key to sign a piece of software, and then you can use the public key to check against it. And the public key will be programmed onto the device from the factory. And that means that any other bootloader that's loaded on there that hasn't been signed with your private key won't run. So secure boot, it doesn't necessarily mean that you can't change the software on it. It just means that whatever you change it to has to be signed. That's a bit of a common misconception, but it also applies to boot modes. So if you're booting off SD card, you can still boot via USB with secure boot enabled, as long as it's correctly signed. That's the key point. And of course, take care of your private keys. If your private key is compromised, then so is every device. And so, yeah, this is a general IT security concern. Examples of chips that implement the above, you're talking about the IMX678 series, the STM32MP1 from STMicro, TI's AM355X, and obviously others. That's by no means an exhaustive list, but these are some that do implement this. So after you have your nice and secure bootloader, then you have the not so trivial task of securing every single piece of software that runs after it in what's called a chain of trust. So just to talk about UBoot for a moment. So this is the name of the most common bootloader for embedded Linux. In fact, you'll find it pretty much everywhere. It's very powerful and it's got a lot of flexibility to help during your design and prototype phase, but that same power and flexibility does need to be locked down when you come to production. For example, there's a command line interface that allows, reads, writes to memory, network access, all sorts. If your attacker gains access to that, then they've pretty much gained access to the whole device. So again, you need to make sure that you disable the console or you disable your debug input. Whatever you do, you need to make sure, obviously, that an attacker is not going to get to that command line interface. Another issue is something called the UBoot environment. which, like on the Linux command line, is a bunch of key value pairs, and these often define the boot flow. For example, where to load the kernel from, what boot arguments to pass to the kernel, where to load the device tree from. And again, great for development, but not so good for security. They're by default, they're just stored with no encryption, just on flash. So you might want to lock these down to avoid a security vulnerability. Setting the config env is nowhere parameter will basically mean that they always get read back from the defaults in C code. Or if you want to use the environment for other things like boot counters rather than boot flow, you can make sure you just lock down all the boot flow variables and cause them to go back to their default states. Okay. So chain of trust, as mentioned previously, every piece of software that runs on your device needs to be signed by a previously trusted piece of software, which is what's called the chain of trust. So that means the bootloader needs to sign everything that comes after, which will be your kernel, your device tree, and your RAM file system. UBoot provides something called a unified image called an FIT image to sign everything at once. That can help speed things up or simplify things, or you can do it individually. It doesn't matter how exactly, but everything that can affect your software must be signed. That's the key thing about that. Right, so yeah, as discussed, the kernel and device tree should both be signed and verified in UBoot. As for the kernel itself, there's certain configuration options that you may want to enable with light security, such as enabling control groups or C groups. They allow you to access resources on a process-by-process basis. Network filtering should be enabled if you want to set up a firewall using IP tables. And any configuration options that would enable a MAC, mandatory access control sort of setup, they should also be enabled. If you want to make use of ARM OPT, then you need to enable that sort of thing. And the device tree should disable the debug UART at least input, and you can see that sort of example of how you might do that in the device tree. Just talking about security patches on the Linux kernel, you want to run a kernel that has a long-term support declaration. This means that any security flaws that get patched upstream will be backported to that version with the LTS declaration. Currently, the 5.10 has an end of life in December 2026. So if you're thinking about what to use now, 5.10 is probably quite a good option. Okay, so the IotRAMFS, which is your sort of initial RAM file system, that's what it stands for. This is typically a small file system that is temporary and mounts the real root file system that you're going to use. However, it can be as large as you like, as long as you've got enough RAM. And if you have enough memory, or if your application is small and has few dependencies, you could put everything in the IotRAMFS and just run from there indefinitely. Obviously, it must be signed, but as it's a single file and is read-only, all software running on it will be secure. So if your entire system is within this IotRAMFS, then your chain of trust is complete and you're done. All software running on the device is now signed. However, in a lot of cases, you're making use of a lot of different open source libraries. You've got a limited amount of RAM. Your application is actually quite complicated. You can't fit everything into an IotRAMFS, and you're going to have to run from some sort of disk. So in that case, the IotRAMFS has to then verify the root file system, and before then changing to the new root file system, has to do that verification, and that's its part of the chain of trust. And yeah, all RAM will be released to the system once you call switch root at the end. Okay. So the root file system, it can be encrypted. There's various kernel modules like dmcrypt, fscrypt that allow transparent mounting of file systems. So you can read and write, and from the system perspective, you don't even know that it's encrypted, but it is. But it depends on the limitations of your platform or file system. You should consider where to store your keys. This is really important with regards to security. If your keys are not, if your cryptographic keys for encrypted volume aren't secured safely, then you can lose all your encryption quite easily. So on some platforms, there's a key that's inside the processor itself, and can never be seen, and is used to do all encryption on the fly. So sort of IMX, some of your IMX platforms have this, some of the chips have this, a sort of internal key that can only be seen by the cryptographic module inside that chip. So it's that's really good. But in other cases, you need to use your TPM to store your key, or some other secure storage mechanism. But yes, if you don't store it correctly, then your encryption can be compromised. Ideally, the root file system will be a read-only file system like squashfs, which will be a single file, and therefore easy to sign and verify. Again, at this point, your chain of trust ends. Any update to the file system will be signed in its entirety. If instead you need to do package-based updates, maybe you've got a slow link and large overall rootfs, and you can't afford to do a full atomic upgrade every time you want to do an update. You can't afford to update everything. It just won't work. Then your chain of trust becomes a lot more complicated. You need to start thinking about how you're going to verify all those separate packages, and this is really tricky. Now you need to verify every single executable, every single script, and every library, and perhaps your config files that mustn't change. And if you detect any infraction, just like secure boot in the first place, you need to stop it from booting at that point. And so again, this will be done in the IotRAMFS. And also, if you do go this way, you must make sure that any accidental change to any files don't cause a false alarm. Again, you can use control groups to isolate access to the file system, and that's pretty good from a security standpoint. So, okay, right, the data partition. So most applications, even if the root is read-only, they need to store some data, and this is normally done in a separate data partition. And you need to make sure that it's encrypted, especially if there's any sensitive data on there. Fairly straightforward. Again, consider key storage and all those sort of things. Okay. Right. So then we've got to think about init systems. So as discussed above, if the entire root file system is signed, then you don't need to worry about verifying all the scripts that are running in it. But if it's not all verified, if it's package based and anyone can just go and add a file, you need to make sure that any file that's added won't get run. Any scripts can't get run by an attacker, because otherwise you've just you've lost it there. A malicious script could be added that uploads all your sensitive data up to the internet. So you need to check which directory scripts are being run from, and checksum and sign the checksums, and make sure that there's just no way that it can be done. So this can get very complicated, especially as some processors can call other scripts and plugins in certain directories. So with embedded Linux, with open source software, you're suddenly now having to audit quite a lot of different things. So yeah, just be very careful. Think about your systemd, sysvinit, where they're getting scripts from. Think about what software you're running underneath that. Things like Watchdog, for example, is not your sort of hardware watchdog, but there's a program called Watchdog, which can call all scripts in a certain directory. You even need to think that far ahead, because any script that's placed, you need to ensure that there's nothing extra there, basically. After checksumming and signing all your directories, and you can start to think that your chain of trust is complete. Just yeah, as we say, just be very, very careful with your audit. And then at that point, hopefully your chain of trust is complete. Right, okay. So system software, SSH, it's a great tool. That's secure shell. It's used to log in over the network into a device and get it command line. But you do need to lock it down. You should disable password-based login and just use key-based only. So again, with that sort of public-private key, you keep hold of the private key and you put a public key on the device and you put it in the authorized keys file, and that means that you can use the private key to log in. But better yet, disable SSH entirely if you can. And if you can't do that, maybe run it off a non-standard port. So SSH normally runs off port 22. Consider just putting on port 5522, something like that. So, okay, if you've got a web server, you want to make sure you use an off-the-shelf solution, something like Apache, Nginx. Check for obvious security holes in your front end. Ensure JavaScript can't execute arbitrary code on the targets itself. So sometimes when you have embedded engineers, they're not necessarily web engineers. They don't always think of all these possible security flaws that you can have. Just remember that any attacker talking to your web server can read every line of front-end code just from their browser. So you just need to be careful that that interface is, again, secure and following all sort of best practices. And you can find a lot of checklists for that online. So other services, same sort of principles. Any other network-facing service, you need to sort of check and follow some sort of audit, some sort of process, and anything that isn't needed, disable it. Okay, so finally, every embedded system normally after the BSB has an application. So to finish off, let's talk about that. So as with the web server, and any custom code needs to be checked for security bugs in the same way you need to do these audits. You need to get the most obvious stuff right. That's what I mean by don't do anything stupid. Just try and follow best practices as best you can. Follow documentation online, follow some other talks that talk about security practices, and get multiple engineers to review. And again, we can lock down things using systemd namespacing or C groups. We can keep permissions, lock down general, Unix permissions, Linux permissions, and if you really want to be hardcore, you can use something like SE Linux to really lock down the app and other parts of the system. But that's somewhat outside the scope of this presentation. Okay, so a few final considerations. Try and follow the general security principles, use standard auditing practices, do some research. These are the most likely to trip you up. Software attack is more likely than a hardware attack, though if there's enough of your devices out there, people are going to start trying to attack it physically. So we're talking about those sort of debug UART and JTAG interfaces. So make sure those are disabled and solid. Just get the basics sorted. Think about your storing your crypto keys properly. Disable any interfaces you don't need, and verify all your software. Secure boot, very important. Okay. Okay, well, thanks very much for listening. And yeah, there's a couple of questions in the chat, so I'll just talk about those. Okay, so there's a question about how does ARM Trust Zone fit into what I've discussed. Okay, so ARM Trust Zone, I think, is something that was brought in. I did mention it very briefly with ARM Opt. So it's essentially a way of running a secure operating system alongside the one you're already running, which has certain privileged access to certain parts of the system. Yeah, it really depends on the implementation and the support for it in the hardware. It can be useful. It's not a silver bullet. You know, you need to make sure you're using it correctly, and it doesn't negate all the other things that we've talked about. It's essentially another version of privilege control or user control, and not user control, sorry, but sort of, yeah, privilege control, where you've got a separate operating system running. And yeah, what it can do is stop a hack in one part of your system affecting a more sensitive part. So it can be useful, but you still need to do things like secure boot and all these other things that we've been talking about. And the other question is just a quick question. Can I say anything about RAM encryption? So yeah, that's there are ways of doing RAM encryption. Obviously, having hardware support for it will have less system impact. But yeah, I believe that some implementations of the ARM trust zone can do RAM encryption. So when you're actually reading your keys, they're encrypted even in RAM. So yeah, that's quite a deep subject actually, and probably something a little bit outside of what I'm talking about here. But yeah, there are some different solutions for that. So yeah, do a bit of research online. It really depends on your use case, how paranoid you are. Yeah. Okay. All right. Well, thank you very much. Thanks for listening. And yeah, with any more questions, please get in touch. Okay. Thank you.